So yesterday we didn't quite get to the examples, but we did end our lesson by talking about the different types of forces of attraction amongst particles. And one of the things that we talked about was sort of the hierarchy or the tier or the ranking of those particles. We said that the strongest force of attraction would be like an ion-ion attraction. We said the second strongest force of attraction would be hydrogen bonding attraction. We said the next strongest would be dipole-dipole. And then we said that the last one would be, or the weakest would be the London dispersion forces. So we're going to use that information to go through these three examples here real quick. And there's a couple of things that we need to be able to do first. So one of those things that we're going to do first is we are going to take a little bit of time to identify what is occurring or what type of molecule we have. So I can tell that that this molecule here is a covalent molecule. And I can say it's a covalent molecule because it's a nonmetal and a nonmetal. So we have hydrogen and oxygen, both nonmetals. I can also tell that because of the partial charge designation here, remember that those things indicated partial charge. Okay. So that tells me that there might be that there's going to be a polar bond present. So there's going to be like a polar bond here. But the presence of a polar bond does not necessarily mean that the molecule is polar. However, in this case, you have to remember that when there is like a delta positive or a delta negative, we could draw an arrow toward that delta negative, and that arrow indicated where the electron was being pulled towards. So if I was to do that here, I would be able to say that the electrons in those polar bonds are being pulled toward the oxygen, right? So because they're being pulled toward the oxygen, and there's these unshared pairs of electrons on the oxygen, we're going to be able to say that this is going to be a polar covalent molecule. It's a polar covalent molecule, and we can say things like, because the arrows don't cancel each other out. Bless you. We can also say that it's a polar covalent bond because there's unshared pairs of electrons on the central atom. So there are a couple of ways that we can identify that this is a polar molecule. Now, the next thing that we would do is we would go ahead and identify the types of intermolecular forces of attraction that are present. And because this is a covalent molecule, one of the things that we talked about yesterday was that all covalent molecules have London dispersion forces. Okay, so all covalent molecules have London dispersion forces, and as a result of that, that's one of the intermolecular forces of attraction. There is one other in this example force of attraction that might be present. Does anybody want to take a guess? Right, this one would be hydrogen bonding. And we can identify that because of the hydrogen bonded with the oxygen. So this is hydrogen bonding. So now the next thing that we're going to do here is we're going to draw two of these molecules and show how they're attracted to one another. So I'm going to draw the first molecule 1 like this. And I'm going to show that the oxygens are bonded to the hydrogen. there is a delta negative charge here, a delta positive charge here, and a delta positive charge here. So we're taking. So I'm going to draw a second molecule here, and that molecule will have the hydrogen or the two hydrogens and the oxygens. But we're going to draw the delta negative and the delta positive and the delta positive. And we need to make sure that we are drawing those because that's what's going to allow us to show the intermolecular force of attraction. So in this structure, the oxygen is attracted to the hydrogen, okay, because the hydrogen is slightly positive and the oxygen is slightly negative. And so that's the force of attraction that we're looking for. Any questions about this? Okay. In example number 2, we have another covalent molecule. Again, because it's nonmetals only. And those partial charges, right? Those partial charges tell us that all of these are polar bonds. Okay, so they tell us that those are all polar bonds. Now, but the issue is that, as you recall, with the partial charge designation, right? If I have a bond that has a delta positive and a delta negative on it, our arrow would draw toward the delta negative. So in this instance, the arrows are drawing away from carbon and into fluorine, or towards fluorine, rather.
What does it say at the end? Non-metals
only.
Oh.
And so then the issue here is that if these arrows that are opposite of each other, they're basically being pulled toward the same atom, and when they're being pulled toward the same atom, they essentially cancel each other out. So even though there's polar bonds, this is still going to be a non-polar molecule. And we can say it because the arrows cancel each other out. Yes.
So I've had this question for a while, right? But for the arrows, why is there like the line?
What do you mean, which line?
Well, it's like, they have the arrow, like the tip of it, and then they got like the random line in it.
Okay, so the arrow points towards the negative, okay? But this little tick right here indicates that that's the positive side of the arrow.
Oh, it's like a plus.
Sort of, yes. Yes, sir. Now, the next thing that we have to do is we're going to go ahead and identify the types of intermolecular forces of attraction. And because this is a covalent molecule, all covalent molecules have which force of attraction? It's the London dispersion forces. And then the next question that I need to ask is, are there any other forces of attraction here?
No, I don't think so.
You are all correct that there are not other forces of attraction in this one. Okay. So when we have a nonpolar covalent molecule that only has London dispersion forces of attraction, the way we draw them is we're going to just draw a circle like this over here and write CF4 inside of it, and a second circle like this over here and write CF4 inside of it. And then we're going to decide that one side of that structure is going to be slightly positive, and one side of that structure is slightly negative, and then slightly positive, and then slightly negative. Now remember, this is when we talked about the weird head on a stick thing, right, at the pep rally, and if the head went this way, everybody leaned this way. And if the head went this way, everybody leaned this way, right? And there's a lot of cheering and all the things that go along with that. Okay. So the issue here is that, or the other thing that's important to consider is that if there are like an entire set of bleachers and there's only like 4 people on those bleachers, the effect of the head going this way and people leaning is significantly less impressive than if it's an entire bleachers full of human beings. So with that in mind, we also have to consider or think about the fact that in this structure, there is one carbon atom that brings 6 total electrons to it. And there are 4 fluorine atoms that bring 9 electrons each, which would give us 36 electrons. And then we add those up, and that becomes 42 electrons total in this structure. Today, or for this example, that's not quite as important, but it will be important in the next part of this lesson. So at this point, we now have said that all 42 of those electrons are like shifting over to this side of that carbon tetrafluoride, and all 42 electrons in the second one are shifting to that side. So what that creates is an area where there's going to be a slightly positive side of one of the molecules and a slightly negative side of the other molecule, and that will be where the force of attraction is. Does that make sense? Okay, the third example. This is going to be one of those good old-fashioned U tries. Give it the old GHS try, real quick once. Ready, set, give it a go. So we're going to pause here for a second. I'm going to ask, what type of intermolecular forces of attraction do you believe are present? LDF is one of them. Yes. Yes, the other one would be dipole-dipole. So with that in mind, go ahead and finish this up. Hopefully you drew something that looks a little bit like this. So in this instance, I had the negative side of this molecule, which is really surrounding nitrogen, and the positive side of the other molecule, which is really surrounding any of the iodines. And those two were brought in close proximity to each other, and then they were able to have the positive, or they were able to have a force of attraction. Any questions about this one? Yes, sir.
For example, for example 2, how do you know one should draw like that model or like a circle model?
Okay. So the question is, how do I know to draw the structure like I drew it here versus how do I know to just draw it as a circle? Okay. The answer to that question lies in the types of intermolecular forces that are present. If it's just London dispersion forces, we draw the circle. If it's London dispersion forces and anything else, then we draw the structure out. Okay. Any other questions? Okay, so then that was the last of the examples. So now we're going to transition into the next part of our notes. So we'll get into that now.